friends, welcome to this new course, the Lebesgue Measure Part 2, and the content named as the Lebesgue Integral. The Lebesgue integrals are the integration of functions over measurable sets which could integrate many functions that cannot be integrated as Riemann integrals or even Riemann-Stieltjes integrals. So the first section is about the Lebesgue integral of a bounded function over a set of finite measure. Bounded function, what is a bounded function? A function which is defined on a set having the real or complex values is said to be bounded if its set of values is bounded. So lesson 1 introduces the definition for the characteristic functions and simple functions. So the first definition is for the characteristic function. If E is any set, then function chi E, this is the new function named as the function chi E, defined by chi E x is equal to, it gives the value 1 if x belongs to E and its value is 0 if x does not belong to E. Right? So this is called a characteristic function of E. Please note over here, the function chi E is measurable if and only if E is measurable. And second thing is, the existence of a non-measurable set implies the existence of a non-measurable function. Let's move on to the second definition about a simple function. A real valued function phi is called simple if first it is measurable and second it assumes only a finite number of values, right? Finite number of values means its range is finite. We can also say this in other words, that phi is simple if, number 1, phi is measurable. If you look at over here, this is your function phi, this is simple if phi is measurable, and second, finite number of values. It has finite number of values, it assumes finite number of values, which means its range is finite. So second, the range of phi is finite. Very fine. Alright. Then is a remark. Suppose I am having two simple functions, phi and g, right? Then their sum, their difference, and their multiplication, their product are simple. Please note this as remark. Okay, now writing phi as a linear combination. Now a linear combination, writing phi x equal to summation ai, that is the values of phi, multiplying with chi ei, right, x, and I is going from 1 to n. So this linear combination is a simple function if the sets ei are measurable. Please note, this representation for phi is not unique. So the next is canonical representation of phi. If phi is simple function and second, it is having the set of non-zero values of phi, that is a1, suppose a2, a3 up to an. These are the set of non-zero values of phi. Then phi is equal to summation on ai and writing here chi ai. I going from 1 to n. ai is a set having all those values x such that phi x is equal to ai. So A1 set is having all those values x such that phi of x is equal to A1. Right? Similarly, A2 is a set having all those values x such that phi of x is equal to A2. Right? So AI is set having all those values x for which phi of x is equal to AI. For such set, phi is equal to linear combinations for chi AI. Right? So summation I going from 1 to n AI chi AI. This is the canonical representation of phi. Provided this set of non-zero values of phi, these should be non-zero values. So phi is equal to, let's open this summation. This is A1 chi A1 plus A2 chi A2, so on, AN chi AN. Right? Let x belongs to A1 only. Right? Then this will be equal to, for x belonging to A1, this is A1, chi A1 gives the value as 1. Whenever x belongs to A1, this will give me the value as 1. We have, in the very start of this video, we have read that the definition for the characteristic function, chi Ex, this will give the value 1 if x belongs to E. This will give the value 0 if x does not belongs to E. And here, because x is belonging to this A1, so chi A1 gives the value as 1 plus, now x does not belongs to A2, x is belonging to A1, so chi A2 will give the value as 0 plus, so on, all the remaining terms are 0. So finally, I'm having phi is equal to A1 if x belongs to A1. Now this is clear, right? Okay. This representation for phi is called the canonical representation of phi. First point, please consider this. If AI are disjoint and small ai, that is the values of phi, these are distinct and non-zero. Right? Then the representation of phi is canonical representation. Right? Please take care of these 2 points. Okay, next is integral of phi. Now what if phi vanishes outside a set of finite measure? If phi vanishes outside a set of finite measure, then we define the integral of phi x dx is equal to as summation ai, I going from 1 to n, measure of ai. Right? Where phi is equal to summation ai chi ai, I going from 1 to n, has a canonical representation. Right? Okay, please look at over here. A remark is given. If E is measurable set, we define integral of phi x dx as integral phi x chi ex dx. This is how the integral should be defined as if E is any measurable set. So it is often convenient to use representations which are not canonical. So the lemma is very useful, which will be discussed in the next video. Thank you.